Okay, so good morning and good afternoon, everyone. Thank you very much for joining our webinar today. We believe that this is a very important case study to share with you and wanted to give you an opportunity to see what we have to share and then give you the opportunity to ask any questions of our team that you may have. Our panelists today are Eric Jensen, Data Aire's Vice President and General Manager, Mike Lawler, our General Sales Manager, and Dan McInnes, our Applications Engineering Manager. We'll try to keep a good pace for the webinar in order to allow time for the Q&A at the end. So please submit your questions to the Q&A folder located on the menu bar at the bottom of your screen, or at least that's where it's normally located. Any questions we don't get to can be submitted to the team afterwards, or you can reach out to your regional sales manager, ask them. Again, we are recording this presentation, and we will repeat it again. We'll repeat it live next month for those people on your team who couldn't attend today. So without further ado, I'll turn things over to Eric, who is going to kick off the presentation today.
Okay, thank you, Carlin. Hello and welcome, everyone. Thanks for joining this latest installment in our Data Aire University series of learning sessions. We've got a great topic today. We have an important set of sales strategies and tactics that we're going to cover. You will learn today what building design challenges led to the need for GeForce Ultra used in this particular application, what application-specific modifications were made to GeForce Ultra, free cooling calculations with local weather bin data to show energy savings, and how you can sell more GeForce Ultra systems. So let's move on to our title page. So the title of our program for today is A New Horizon for One Wilshire, Economization Solutions for Today's Modern Data Centers. It really is a landmark case study for all of us who promote and sell Data Aire. One Wilshire is an iconic building, and we're going to cover how the challenges of this project have unleashed an unprecedented solution to the market, introducing you to ways you can take advantage. But before we launch into that, we're going to take our first poll question of the day. So Carlin, if you would launch our poll question, please. I will read it for the crowd and ask that everybody participate with your responses. Okay, here we are. So, GeForce Ultra selling points. Question is, what do you consider to be the most effective selling point of GeForce Ultra? This is multiple choice. Discharge air temperature control, turn down ability and load matching, variable speed compressor and DC fan synchronized control, D, energy efficiency. If you would please take a moment, give that your thoughts to the extent you need to, and record your response. Give just a few seconds to complete this before moving on.
And I see that we have about half of the people have voted, so we'll just give you a little bit more time.
All right, 10 more seconds. There's no wrong answer here. Okay, Carlin, why don't we close this out? All right, so what we'll do is we'll come back to those results later in the presentation. So now I'd like to get into the case study itself on One Wilshire. One Wilshire is a high-rise carrier hotel developed directly atop North America's Western Fiber Hub. It is in downtown Los Angeles. A couple of quick fun facts. It was built in 1966. It is one of the first new high-rise buildings built in downtown LA after the height cap was lifted in 1958. It's 30 stories tall, 662,000 square feet. In 2013, the building was purchased by GI Partners, who paid $437 million for the building, which at the time was a record price per square foot, making it the most expensive commercial real estate out there. It has 21 megawatts of primary power and 4,400 tons of two-end centralized condenser water loop. One Wilshire is highly regarded as the most densely connected building in North America and one of the top 3 telecom centers in the world. 1 in every 3 bits of information from Asia pass through the undersea cable that terminates at the base of this building. So as I mentioned, One Wilshire sits atop the fiber optic cable backbone that comes in from Asia. And it was originally conceived as an office building. Because it was an office building, there were several complexities and challenges in developing a master plan that really brings a 1960s era Class A office space into modern data center office space. Oh, we seem to be moving our slides backwards. Forgive me for that. All right, we're back on track. So there was no available space really to route much of the infrastructure when they conceived of what their master plan needed to do to bring this into the modern era. The primary challenge was to develop an effective solution with limited utility space, limited space for cooling, limited space for installation, for crating, carting, etc., lay down areas, all of the normal parts and pieces and procedures associated with building what is a modern data center. However, because of its location strategically, there was no other option for locating this dense connectivity because of the way that the fiber backbone comes in from Asia and terminates at this location, because many end users require such low latency for particular applications. So to meet that demand from the marketplace, this is where data centers needed to be, and as a result, the challenges needed to be resolved. So they needed a plan. The team developed a master plan and subsequent building upgrades that allow new tenants to come in and take advantage of that connectivity, as well as the improved infrastructure that is designed and installed into the building as of now. So to kind of take a little bit of a step back, the primary players associated with this, as I mentioned before, GI Partners had acquired the building and is the property manager now. They took over the building from CoreSite, who is a data center REIT, but they also are a data center colo provider as well. They were the primary tenant and still are one of the primary tenants in the building. The building is about 70% data center at this point in time, and so there's plenty of additional opportunity for the owners to convert still existing office space into data center, which of course bodes well for those who are looking to supply infrastructure into those kinds of markets. So the challenges beyond space constraints associated with bringing in 4,000 tons of what needed to really be scalable cooling to bring 70% data center to 100% data center, which is the plan, as well as 20 MVA of utility and generator power. So it is designed to Tier 3 standards from the Uptime Institute. And so scattered about some of these photographs, you can see just little snapshots into the really what the designers and the owner, as well as the contractors who had to execute on the project, were faced with. There's a low roof at, I believe, the 4th floor, but there's also, of course, the top floor, the roof, 30th floor, that each of which was fully occupied. So as you can see, there's a smattering over the decades of different types of equipment because each tenant was left to its own devices. And really, this whole master plan was an intent to centralize the infrastructure from a power and a cooling perspective and standardize for the tenants moving forward. So those goals included expanding the power and cooling beyond what they are today, centralizing it, as I mentioned. They needed flexibility for future needs because no data center can be future-proof enough given the rate of change. And they wanted a solution that, of course, couldn't interrupt all the existing tenants. All of this occurring downtown LA. That last piece that I hadn't mentioned up until now is 50% free cooling. And that really is the nature of what we want to talk about here today, is they set a lofty goal for themselves of achieving 50% full economization for a downtown LA data center built in 1966, essentially. So we'll start with some of the electrical, just briefly, and then, of course, transition into the cooling. So you can see on the left-hand side there is a short alleyway, which is really their access for being able to plop down 20 or 21 MVA of backup generator space for this centralized infrastructure. All of this 21 MVA or megawatts, depending on how you look at it, of course, converts itself eventually into a heat load that must be cooled. And that's where we move into what did the designers go out to market asking for, and what did they get in responses? And so that's where I'd like to introduce Mike Lawler, who's going to talk about exactly that. Mike, are you with us?
I am here. Let me unmute myself. And let's move to the next slide. There we go. Oh, overshot it. Good. So now, thank you, Eric. Carlin, do you want to show the results of Eric's poll question now, or do you want to save that till later?
We'll save that till later.
Okay, good. So now we're going to take a closer look at the equipment itself that was used on this project. The engineer cast a wide net to consider several economizer alternatives to try to hit that 50% of the hours of the year with no compressor running. A well-known option, of course, is the pumped refrigerant economizer. This has been touted as the most efficient unit available, but this statement is speculative. No proof of this was offered. But if you're the status quo and the 800-pound gorilla, you can try to get away with making a statement like that. Your job as data air representatives is going to be to not let the competition get away with a blanket statement like that. If we take a close look at a calculator that our competitor publishes on his website, however, you'll see that the pumped refrigerant economizer is not as efficient as it is sometimes hyped up to be. But before I show you that calculator, I have a poll question that I would like you to answer, and you'll have 30 seconds to answer it, just like the last one. And that question is, dun, 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 dun. What was the answer when Swanson Rink asked our competitor on this project, what percentage of annual hours will the pumped refrigerant economizer deliver full load capacity without compressor operation? So what percentage of the annual hours will the pumped refrigerant economizer deliver full load capacity without operation? Choices are 8%, 32%, 62%, and 76%. Okay, give you a little bit longer.
So about 59% of you have voted. So maybe just another couple of seconds. Okay, I think we've leveled out. So I'll go ahead and end the polling now.
Okay. Very good. So the Swanson Rink team had several requirements for the equipment to be used in the One Wilshire building. And they're shown here, some of them are. With standard equipment, both ours and our competitors, the only requirement that we could meet was the one for the two-way valve. So every project has a unique combination of location, building load, and climate, and all of those were considered by Swanson Rink to arrive at the best solution. Swanson Rink took extra time that a lot of engineers don't take to really dig for the best solution. Most engineers will tend to take the path of least resistance when selecting a system, and your job is to provide some resistance to the path of using a pumped refrigerant economizer, and we're going to show you how to do that. Okay, come on. There we go. This is a screenshot of the pumped refrigerant economizer calculator on our competitor's website. As you can see, we selected Los Angeles as the city, so the analysis will use LA bin data. We changed the return air temperature to 95 degrees, which was what the One Wilshire building job called for. And based on that assumption, this shows compressorless cooling by our competitor 62% of the year. That's pretty impressive. That's the purple. The green area is the times that one circuit will be operating on compressor and the other circuit of the two-circuit machine will be operating on economizer. So 33% of the time, you'll get integrated economizer. That's not bad. But note that the calculator defaults to 70% unit load. This is the key input that makes these results from our competitor look so good. So the competition will try to convince the engineer that 70% load is full load. And they have lots of reasons they'll try to use to justify that. But the reason for doing that is shown on the next slide when we make the percent unit load 100%. So now this is percent unit loaded 100%. Notice that now compressorless operation has dropped down to 13% full economizer, 48% partial economizer, and 38% of the time they have no economizer at all. So I'm going to ask you to write important things down at several points of this discussion, and here's the first one. So write these two things down. 1, convince the engineer that full load is 100% design load, not 70%. This shows data Aire in the best light and our competition in the worst light. So this is what you should drive for. And number 2, talk to the engineer in terms of hours of compressorless operation rather than talking in terms of operating cost or energy savings or TCO. Going down that road really complicates the conversation, adds a bunch of variables to the analysis that are subject to manipulation, just like the percent full load number was manipulated. But if you look at TCO, you've got dozens of numbers that can be manipulated. So keep it simple. Simple is elegant. Simple is memorable. So the engineers can hang on to this.
Hey, Mike.
Now,
sorry to
yes.
jump in. At what point did you want to share the results of that survey?
Of the poll?
Yeah.
Oh, we can share them right now if you'd like to.
Let's do that, because I think that's a very important point, that when we went to 100%, it showed us at 13%. And here is what, let's see, is this sharing? There you go.
Okay, good. So 8%, 32% was the big winner. 62 and a few thought 76%. Quite interesting. Okay, we'll tell you what the actual number was later on in the presentation. So this is, let's take a closer look at data Aire site-specific solution and how we met all of the owner's goals. So at the time Swanson Ring brought us into the project, data Aire didn't have a system that met their criteria either, but we were willing to work with the engineer to develop one, and all of our competitors passed on that opportunity. So here's what we did. To minimize the risk associated with designing a completely new unit, we started with our dual cooling unit, which is a tried and true technology, and then we optimized that unit for the 21st century data center conditions. So dual cooling units have 2 cooling coils. One's a refrigerant coil that uses the compressors to make cooling, and the other coil is the energy saver coil that uses water from the cooling tower for free cooling. We made a lot of other changes, though, to achieve Swanson Ring's goals. We replaced high pressure drop coils with low pressure drop coils, both on the air side and the water side. We replaced the valves in the unit with lower pressure drop valves. We changed the internal piping to take advantage of every gallon of water from the cooling tower. We oversized the chill water coils and the condensers to provide maximum free cooling hours and to require minimum pump horsepower. And we tweaked the control sequence to expand the number of free cooling hours. And most importantly, we used a variable speed compressor operated by a VFD for the compressor in the unit. So the result was an enhanced dual cooling unit based on our traditional GeForce Ultra platform. Now let's take a look inside this unit, and I'll show you where the components are located, how that comes together. There we go. So here's a photo of one of the units for this building while it was in final test at the factory. So up here, this was our oversized energy saver coil. The energy saver water coil is on the outside. The DX refrigerant coil is behind the energy saver coil in a nested A-coil arrangement. Below that are the direct drive plenum fans. Each one has its own plenum. This increases efficiency, and it allows each fan to be pulled out individually for very easy changing of the motor. Here is the water regulating valve. Normally we have one water regulating valve, but in this unit, to save space and reduce pressure drop, we use 3 valves in parallel. And this is the water-cooled, the variable speed scroll with variable frequency drive. That shiny box above the compressor is the drive. And here's the hinged electrical panel that swings out of the way so that only front access is required for service and maintenance. So here's another one. Here's another one. Write this down. The unit's refrigerant circuit in a water-cooled unit is factory pipe, and it ships fully charged. Factory piped, ships fully charged. So what that means is no refrigerant piping is done in the field, no refrigerant charging is done in the field, so there's no opportunity for the installer to get those things incorrect. So we've eliminated the potential for mistakes. Now we're going to look at the circuit itself. So the unit has 3 modes of operation, but only 2 modes will actually be used on the one Wilshire building. So this mode shown here, this is the compressor assist mode. So what that means is both compressors, both the compressor and the energy saver coil will operate simultaneously to minimize energy usage. So we start at the cooling tower, go to the pumps, we come into the building, and we go past the chill water temperature sensor that controls the chill water valve on the right. The chill water sensor, when the sensor sees water from the tower that is between 67 degrees and 74 degrees, then the system can get some economization, but it can't provide 100% load. So what we do is the flow splits here because the chill water valve modulates down, and then some of that flow goes and cools the water-cooled condenser so that the compressor can operate at the same time you're in free cooling. This was a real important innovation, saved lots of energy. Once the water has done its job in the condenser and the energy saver coil, the 2 flows come back together, and it goes back to the tower to repeat the process. The next mode of operation we'll look at is no compressor operation at all. So anytime the chill water sensor sees water temperature 67 degrees or less, then we don't need to run compressors at all. So the controls will see that. They'll push all the flow through the energy saver coil. Then it goes back to the tower and repeats the cycle. So this is the no compressor operation mode. And the last mode that it has is the variable speed compressor only mode. Now actually on one Wilshire, we never have to operate in this mode because the entering chill water temperature from the towers actually never gets above 74 degrees Fahrenheit. But in this mode, this is just a typical water-cooled DX unit mode. All of the water goes through the the water-cooled condenser. The compressor runs, and we don't do any economization at all. So, by the way, we show single circuit units in these drawings because that is what we used on our first job that we did at one Wilshire for Z-Colo. Since then, we've done a second job at one Wilshire. The customer was CoreSite, and CoreSite wanted fewer units that were larger. So we also offer this with 2 variable speed compressors instead of 1 variable speed compressor. And those units are extremely efficient as well. So this slide shows the compressor, a curve for the compressor. So we've talked a lot about an economizer, but we can't forget about the compressor. The compressor needs to be as efficient as possible because it may operate thousands of hours a year depending on the weather at the site. And this slide compares energy consumption of a digital scroll compressor and a variable speed compressor operated by a VFD. So as you can see, the variable speed compressor doesn't really save a lot of energy between 25% load and 100% load. The variable speed compressor, on the other hand, begins to save energy as soon as it slows down speed, and at 25% load, it draws 90% less energy than the variable speed compressor. So quite an impressive number. This is why we use variable speed compressors in GeForce Ultra. Here's a graphical presentation of the power consumption during these three modes of operation. So the green line, let's go back. The green line shows that only the fans in the CRAC unit are running. So the water temperature is between 55 and 67, and only that fans in the CRAC unit are running. The blue line shows that the compressor starts and the power consumption increases as the compressor speeds up to meet the increasing load. And then finally, we hit 74-degree entering water temperature. That's the orange line. We have to turn off the economizer, and the compressor runs and ramps up speed by itself to meet the load. So these are the three modes of operation. So I want to talk a little bit about outcomes. Most states now require, and all will soon require, that some kind of economizer be used on every data room. California is famous for having an aggressive energy code called Title 24, but even Title 24 only requires 70 hours per year on waterside economizer. That's that little tiny column to the extreme left. If it's an airside economizer, Title 24 requires 1,918 hours of operation. So you can see, compared to what is normally experienced, the one Wilshire goal of half the operating hours with no compressor was quite aggressive. But our actual performance after we were done designing the equipment is we stay on economizer only, no compressors, 6,238 hours a year, almost 3/4 of the year. And in the remaining portion of the year, it's 2,500 hours of partial economizer, partial compressor runtime. So the data air solution exceeded the goal by we exceeded the goal of 50% by delivering over 71% economizer hours. Another way to look at that may actually be a little simpler is we can look at the runtime in each mode in terms of days per year. So we have 0 days per year with compressors operating, no economizer. We have 105 days per year at one Wilshire with partial economizer, and 260 days a year we're on full economizer with no compressor operation. So you might say about now that this is great, but this job is in LA, and LA has perfect weather for a waterside economizer, and you may be wondering how this will work in other locations that are hot and dry or hot and humid. And the answer is, in almost every case, you'll get significantly better operation or hours of operation without compressors from this water side economizer than you will from Liebert's competitor's dry bulb economizer. So the pumped refrigerant economizer depends on the difference between the outdoor dry bulb temperature and the return air temperature. The data air solution, on the other hand, depends on the difference between the outdoor wet bulb temperature and the return air temperature. So that is a much cooler temperature to look at. So the dry bulb design in LA is 91, and the wet bulb design is 70. But if you go to Atlanta, the dry bulb design is 94, and the wet bulb is 74. So 70-degree wet bulb versus 74 is not that much different. The wet bulb design is also 74 degrees in Dallas and in Phoenix. So this solution will work well in those hot areas that couldn't even think about using the dry bulb economizer of a pump refrigerant. It just wouldn't run nearly enough hours to ever pay for itself. So with that, we'll move to the next slide. Now, by now, hopefully you're really interested in this solution and you're wondering, what does this cost? And the answer is that Data Aire's site-specific solution costs the same, and it usually costs less than a pump refrigerant economizer. So the entire package solution with the pumps, with the tower, with the CRAC units is going to cost less than our competitor's pump refrigerant economizer. So here's something else. Write it down. Costs the same or less than a pumped refrigerant economizer. Now we show PUE here. PUE is power usage effectiveness, and it's a measure that data center people throw around a lot. It involves the power usage of the air conditioning and the other systems in the building, primarily air conditioning, divided by the amount of energy that the datacom equipment in the server rooms use. So a PUE of 2.0 is horrible, but it's very common. A lot of data centers are operating at that level. More commonly, a good data center is going to operate at a PUE between 1.5 and 1.7. Those are very common numbers. So one last time, write this down. Full load PUE of this system is 1.2. That is a really, really low PUE, and there are not many data centers out there that can approach this level of efficiency. So in closing, I will say that this project really demonstrates some of Data Aire's best features as a company to work with. Data Aire is agile and responsive to the customer's needs. We were a consultative partner that added value to the project in the back and forth conversation with the design engineer. And finally, Data Aire thinks outside the box, and we encourage you to do the same. So now I'm going to turn the mouse over to Dan McGinnis, our Manager of Application Engineering, and I will let him take over now.
Okay, thank you, Mike. Just put in the request to Carlin. There we go. All right. Okay, so the next question on your mind, like Mike said, is how will this optimized GeForce Ultra solution perform in other major cities? And the other question that you might be thinking is, how did we come up with the number of hours of free cooling? So I'm going to go into that and explain what bin data is. So this first example here I'm showing is Ashburn, Virginia, which is considered a national hub for data centers. And to calculate the energy usage and percentage of free cooling, what you have to do is look at the bin data. And if you haven't heard of bin data, this is basically the bin method was developed from historical weather data for a particular location, and the number of hours that a certain location experiences temperatures within specified temperature ranges or bins is recorded. So what you see here for Ashburn is dry bulb temperatures and dew points throughout the year, and obviously it's higher here in the summer and lower in the winter. But what we really need for the calculation is the number of hours that this site sees in each one of these temperature ranges. So these are the bins here that you see over on the right. So once we have this, the number of hours, as well as the wet bulb temperature at each of these bins, the average wet bulb temperature, we can come up with a calculation like this. Next slide here. So this is what the calculation looks like. And there's a lot here. I'll break it down. Over here on the left is those same temperature bins we just showed for Ashburn, Virginia. Here's the wet bulb temperatures as well from the bin data, and then the number of hours that the site experiences these temperatures. And the way this table is broken down is color-coded based on those three modes that Mike talked about. So one is the fluid economizer mode. So this is your full free cooling in green. The blue here is the compressor assist, where you need the compressor on at minimum speed, or one of the compressors if you have two. And the orange here is the dual compressor mode, or full DX mode. So as you can see here, big percentage of the year for Ashburn, 65% of the year, you can get free cooling, and even more if you consider the compressor turn down here, 9.8% in compressor assist mode. So what we did is, because this is a cooling tower, and I saw one question in the chat already, it is a closed circuit cooling tower at 1 Wilshire, but it does have evaporative cooling as well, so they spray water on the outside of the tubes, of the closed circuit tubes. So with that approach, you can actually look at the entering water temperature to the CRAC based on the wet bulb temperature. So we take this wet bulb temperature, we use a 10-degree approach, which is pretty typical for cooling towers, and that's how we get our entering water temperature to the unit. So this unit, for example, was designed, like Mike said, for full free cooling at 67 degrees. So that's why this is the cutoff point, 67 degrees here. And you'll see the compressor kilowatt is 0 for this section. It ramps up a little bit in the compressor assist, and then it's on here full load like a fixed speed compressor here. The evaporator fan, we just assume constant speed for this analysis, so it's constant throughout the year. And then here's your total power. So here's the cooling tower. This is a percentage of the year with the cooling tower. We also look at it with a dry cooler as well. You get a little bit less time of the year with a dry cooler because it's using the dry bulb temperature. So you'll see the differences when we look at a couple of different cities here. This is a similar graph that Mike showed, but this is for Ashburn, Virginia. So this is the fans only in the energy saver mode, compressor assist, and the DX mode. And the purpose of this graph is to really show you the scale of how much higher a fixed speed DX or variable speed DX is how much higher the power requirements are versus these drop down modes, which is compressor assist and energy saver mode. So next, Los Angeles. So this is the one we've been talking about the entire presentation, but this is how this one turned out. 73% of the year in free cooling. We actually estimated 1.5% of the year would be full DX, and what we found after their first full year of installation, they actually never needed to use the full DX mode. They did go into compressor assist, but our analysis was slightly conservative because we never reached this point. So this was actually 0% of the year needing full DX mode. And in this case, using a dry cooler would have lost you a decent amount of percentage of the year, as we were able to take advantage of the dry conditions in Los Angeles. Similar story here, this chart we've seen here, but this has a much greater entering water temperature range for the compressor assist mode for Los Angeles. But similar story in other cities. So this is Seattle. Obviously, Seattle is much farther north, so you get higher percentage of the year free cooling. But even in other places where they're traditionally like one of the hottest places in the country, Phoenix, Arizona, the dry bulb temperatures are very hot. So if you use a dry cooler and you try to use this approach, you won't get a high percentage of the year with free cooling. But with a cooling tower, using the evaporative cooling approach, in a dry location like Phoenix, you can still get a high percentage of the year, and in this case, half of the year, which is a really big deal for a hot place like Phoenix. Using a cooling tower, half the year getting free cooling out of Phoenix. So, so the last part here, we're going to do one more poll question. Carlin, would you mind starting that? The poll question basically is, are you beginning to see how a solution such as this is broadly applicable? And it's a yes or no question. I just want to see if there's anybody out there that's still, or how people feel about this after what we've said. So we'll give you a few seconds here.
Okay, thank you very much, Dan. Thank you also, Mike, for sharing the ins and outs of this particular solution. And it's evident from the responses to, Dan, your last question there, that some of the stuff that we displayed and presented is kind of beginning to get some juices flowing, hopefully. So let's move into some of the key takeaways for the project. So, lessons learned, project specific as it relates to the case study. Success is built through collaboration and working through the challenges, of course. Nothing new to the audience here. This solution's got a pretty broad reach beyond just LA. Even an urban edge data center. Edge data center, kind of a buzzword, but even an urban edge data center can rival a greenfield data center in its efficiency. And this goes back to what Mike shared about achieving a 1.2 PUE. That's a tremendous PUE, and I can tell you from direct experience that there was a lot of raised eyebrows when this was presented to an all data center industry at a national conference last year. So some of our takeaways really were, forgive me, let's move on. There we go. Some of our key takeaways to the project were that it's a site-optimized GeForce Ultra economization solution. So it's really two different things. We take our GeForce Ultra platform, we add in dual cooling economization, and as a result, we get a very cost-effective, highly efficient, and tried and true platform solution for owners, end users, operators in this space, far more so than what is the status quo. Ask us for assistance. Contact our engineering team. We can help through the sales process. That's what we're here for. This is what we want. This is what we do. Engage in the energy efficiency conversation. That was one of Mike's takeaways that he asked to write down. I think it was his number one. Engage in the energy efficiency conversation. Force a little bit of dialogue rather than taking for granted what may be published, what may be stated. So with that, let's go back to Mike's original poll. I don't think we shared the results for his question. I think, Carlin, we have, right. So if we recall, what was the answer when Swanson Rink asked our competitor on this project, what percentage of annual hours will the pumped refrigerant economizer deliver full load capacity without compressor operation? So these are the results from everybody who didn't really have enough information to be able to come up with a quote-unquote right answer, fully understandable. The responses are kind of interesting here. But what Mike displayed to us is that when you go onto that calculator, you get 62%. Is 62% what they got? Actually, what they came back with as a response to Swanson Rink, the MEP designer on the project for GI Partners, the property owner, was 8%. So the status quo responded with 8% versus a goal for the project of 50%, when in fact what they got delivered to them by data Aire through this solution was 72%, 8.5 months of the year. All right, so let's move on to our last poll question, if we can. Carlin, do we have that available to us?
We do. Do you want to share the results now?
Yep. All right. So, we asked at the beginning, if you recall, what do you consider to be the most effective selling point of GeForce Ultra? This is before we launched into the case study. There's no wrong answer here. The highest response is variable speed compressor and EC fan synchronized control. That makes a lot of sense. It's really not all that different, frankly. It depends kind of on how you read it, from turn down ability or load matching. Energy efficiency, way up there as well. So the hope here is that you can see through the presentation that both are the right answer. It's just a matter of who are you talking to and at what stage of the sales process for what project. So we've got a number of resources here available to you as promoters and sellers of data Aire. Please visit our website, come to digest and understand what we have published available to you via the Rep Lounge, as well as public to the website. The invitation here is please come understand what is there and what is not there, perhaps, and we invite you to engage with us on what you think may possibly be missing so that we can all improve. I'd like to come back and do a quick little shout out for those who were involved in this project. As I mentioned, the key players at the outside of us and our network were GI Partners, the property owner and manager. The MEP designer was Swanson Rink. The tenants were Z-Colo and CoreSite. And I'd also like to give a shout out to our reps who were involved. CFM Company, thank you very much, and Gilbar in New York. Thank you very much to both of you for being part of this solution. So with that, I'd like to roll into any Q&A portion.
Perfect. Thanks, Eric. So we have a couple of questions here. I'll go ahead and read them out. And if we don't answer your question, feel free to go ahead and type it in or *6 yourself and unmute so that you could ask your question. And I know that one of these was answered by Dan. I'm not sure which one, so I'll just read the question and the team will answer. So, do you take any special water treatment precautions to avoid fouling the plate and thin condenser coil?
Okay,
So,
well, Carlin, oh, go ahead.
Oh, go ahead, Mike.
Sorry. Okay, yeah, I'll take that one. So in this case, they used a closed-circuit evaporative cooler. So the coils were only exposed to closed-circuit water that was chemically treated like they're always chemically treated. In other areas of the country, we didn't have to worry about glycol in the system in Los Angeles. But in other areas of the country, you will need glycol. And in those areas, instead of using a closed-circuit evaporative cooler, it might be less expensive to use an open cooling tower and a plate heat exchanger. And that way, we don't have to have glycol in the system, and that'll increase the efficiency and the number of hours that you can operate on compressorless. And I forgot to mention one thing during my presentation that I want to mention here, and it's really important, and that is that our competitor offers a packaged solution, and the engineer likes that because it reduces the time, it reduces his design time. He just specifies pump refrigerant economizer and he's done. So to compete with that, it's really important that you present this as a packaged a solution, including the pumps, including the cooling tower. You need to assure the engineer that you're a one-stop shop for this entire solution. So if you have towers and somebody who makes pump skids in your product line, great. That makes it really easy because the engineer only has to talk to you. If you don't have those other items in your product line, let us know, and we have some connections with Marley for cooling tower and other connections for people that can provide you with pump skid pricing. But really important, it's a total package solution and you're a one-stop shop. We don't want the engineer to talk to anybody but you. If he's got to call the pump guy and he's got to call the cooling tower guy, this is going to take a lot more of his design time and he's going to resist our solution.
Great, thanks, Mike. So we're at the top of the hour. If anyone can stay on, we do have a couple of other questions that we'd like to answer. So feel free to stay on the line. If you do have to get off for another commitment, we understand, but would love you to stay on. So a follow-up question to that last one was, has there been an analysis completed for the northern climate, lower temperatures, using a 30% glycol solution?
So we haven't done an analysis with a 30% glycol, but we can. So David, if you have a specific location, and maybe even some site conditions that you want us to consider, we can put that together for you.
Okay, next up, is the tower open circuit?
That was the one that I jumped in and answered. That's a closed circuit tower, so we've covered that one.
Perfect. Is there an oil return mode on the compressor if it operates at low load for long periods of time? And then follow up to that was, what was the final running load in the space? Is it significantly less than the design? I think we did go over that in the presentation.
The oil return, so the compressor does have a boost cycle. One is you can set it on however many number of hours to just come on and do the boost regardless of operating conditions. And the other version is if it's operating at low load for a certain period of time, and I think it's like a half an hour, it'll do an automatic boost cycle. So yes, it does have that oil return protection.
Yeah, Dan, do we also have a oil separator in there in the water-cooled units?
We do. Yes, we do have
an oil separator as well.
Good point.
Okay, one or two more questions. What was the set point at One Wilshire? Did we go over that?
We did. It was 95 degrees return air.
Well, the set point, though, we used a leaving air temperature set point to control the equipment. And so the leaving air temperature was 74 degrees that we maintained. And so they essentially just flooded the space with 74 degree air and brought the air back brought the return air back as warm as they could get it with hot out, cold out arrangement.
Okay, and finally, John Winslow is asking if we have energy efficiency expectation for the hot and humid zones. So we did have Phoenix in there. We can get some other data. I think Dan had mentioned earlier. We're working through all of the bin data. This does take a little while, so be patient with us. But if you do have something that you're working on, we're very happy to assist you. I'm going to close out the Q&A. Of course, you can reach out to anyone on this team, or you can reach out to your regional sales manager to continue the conversation. please, again, make sure to look at all the resources in the Rep Lounge and reach out to your regional sales manager and let us know if we've failed to provide you with something that you need. We're obviously working towards getting more and more content to help share the value of this solution. We'll be hosting this webinar again in a month. I think I mentioned that at the beginning, so we'll host it live again for teammates that couldn't attend. But we're also hosting this for the engineering community externally on March 26th through Consulting Specifying Engineer magazine. They'll be promoting that. And then again through Mission Critical magazine in June. So we will send you the registration link for you to forward to your engineering contacts. Please look for that in the advisor. If you are not getting the advisor newsletter, please let us know. Please look in your junk, spam, anywhere. It's neither of those things. It's not junk, it's not spam. And go ahead and whitelist us. You can look for dataaire@dataaire.com. That's where it comes from, or marketing@dataaire.com. And if you do want to share this presentation with engineers prior to the upcoming presentations through the publications, please reach out to your regional sales manager. They can work with you to give this presentation beforehand by request.
Okay, I see a couple of other, good. I see a couple other questions that I'll just run down quickly. One, is there a PDH presentation available? Yes, there will be. We have one now that is available, the one that we presented to Data Center World, Data Center World, to the engineers there. That had to be agnostic, so that is arranged. Let's see, what is the system restart time? The system restart time is about 3 minutes, and you can dramatically shorten that by, it's 2 or 3 minutes, and you can dramatically shorten that by ordering the capacitor restart option on the controls. That's a capacitor that will keep the controls themselves alive for through the power outage and until the generator starts. And that I think that has about 90 seconds worth of standby power. Plenty of time to get the generator started. In Ashburn, only the fan energy was considered. Only the fan energy was shown on the graph. We focused on compressorless operation, and the analysis of adding those pumps and cooling tower fans would be a little different. But we did not go into that. That's why we focused on compressor-free operation rather than energy savings. But if an engineer wanted to get that deep into the weeds and the energy calculations, we can provide that information for him. And I think that covers most of them. So I'm done.
Eric, did you want to close us out?
Okay, thank you all very much. Appreciate everyone's attendance. And one final note, I did fail to mention, purely because it seemed so obvious to me, but shout out to the Los Angeles representative for Data Aire, KSR, as well, for their participation in the project. So thank you all to our team, our greater team, including our representatives, our partners out in the marketplace, as well as those of you who took the time to digest this information and will continue the conversation. Everybody have a wonderful day.